A liquid ring vacuum pump looks simple because there is no metal-to-metal compression contact inside the working chamber. That simplicity is exactly why engineers often underestimate it. You see an impeller, a casing partly filled with liquid, an inlet, a discharge, a separator, and perhaps a recirculation pump. But the real machine is the complete thermodynamic, mechanical, piping, instrumentation, and control system around it. If any part is specified loosely, the package may start yet fail to deliver stable vacuum, acceptable vibration, reliable containment, or predictable operating life. Engineering begins with the operating envelope. Do not specify one rated point and assume the vendor will handle everything else. Define the normal operating point, rated point, startup condition, minimum and maximum flow, suction and discharge pressures, gas and ring liquid temperatures, recycle operation, transient conditions, and every credible off-design case. The vendor must know where the machine normally operates, where performance is guaranteed, and what it will experience during startup, shutdown, turndown, and process upset. A machine selected only for the rated point may become overloaded, unstable, inefficient, or thermally limited during everyday operation. Next, agree the properties of both the process gas and the ring liquid. For the process gas, define composition, molecular weight, saturation condition, condensable content, corrosiveness, toxicity, flammability, entrained liquid, solids, and expected contaminants. For the ring liquid, define composition, vapor pressure, density, viscosity, operating temperature, compatibility, contamination tolerance, and corrosion behavior. These properties govern capacity, achievable vacuum, absorbed power, metallurgy, sealing, separation, cooling, and reliability. Higher ring liquid temperature increases vapor pressure and reduces vacuum capability. Condensing vapor increases heat load. Solids may erode the impeller, obstruct recirculation passages, or contaminate mechanical seals. Corrosive components may attack the casing, impeller, separator, piping, and auxiliary equipment. You cannot separate process engineering from rotating equipment engineering on this machine. Now examine casing connections. For flammable or toxic service, threaded process connections should not be accepted. They create additional leakage paths and depend too heavily on assembly quality and long-term thread integrity. Use robust flanged or otherwise approved connections suitable for the service. Apply the same discipline to vents, drains, instrument takeoffs, seal connections, and auxiliary piping. Small bore connections often fail first because they are lightly supported, exposed to vibration, and frequently modified during installation. Every connection must be reviewed for containment, accessibility, support, vibration resistance, and maintainability. Then address external forces and moments. The manufacturer must state the maximum loads that the casing and machine nozzles can withstand without distortion, misalignment, excessive vibration, seal failure, bearing distress, or loss of performance. For a packaged unit, the vendor must also state allowable loads at the customer connection points. Those loads must be translated through package piping, the separator, valves, supports, and skid structure so that machine nozzle limits are never exceeded. Poor piping flexibility can distort the casing, shift the shaft centerline, increase bearing loads, open seal faces, alter internal clearances, and increase vibration. A machine may pass every factory test and still fail after site piping is connected. That is why piping stress analysis, support locations, thermal growth, flange alignment, installation tolerances, and equipment allowable loads must be coordinated before installation. Never use flange bolts to pull misaligned piping into position. Mechanical shaft seals require equal discipline. Use cartridge-type mechanical seals because they control setting dimensions, reduce installation error, and improve maintenance repeatability. Check seal face materials, elastomers, metallurgy, operating pressure, temperature, solids tolerance, leakage handling, flushing, venting, draining, and accessibility. The seal must be compatible with both the process gas and the ring liquid. Seal failure can draw atmospheric air into the process, release hazardous material, destabilize vacuum, contaminate the ring liquid system, or create a flammable mixture. Seal reliability is not merely a maintenance issue. It is part of process containment and operating safety. Now consider machine dynamics. Rotating components must be dynamically balanced to a suitable precision balance grade. Residual unbalance increases bearing loads, vibration, seal movement, fatigue, and noise. But balance quality alone is not enough. The fully assembled machine must demonstrate acceptable vibration during testing and field operation. Vibration should be measured in all relevant directions on the bearing housings. Record horizontal, vertical, and axial readings where applicable. Also record machine speed, load, suction condition, discharge pressure, ring liquid flow, ring liquid temperature, and bearing temperature. A vibration value without operating context tells you very little. If field vibration exceeds factory values, do not immediately blame the rotor. Check soft foot, baseplate distortion, grout quality, piping strain, coupling alignment, hydraulic instability, gas slugging, ring liquid flow, bearing condition, foundation flexibility, and structural resonance. The factory test proves that the machine can run correctly. Field performance proves that the installed system has been engineered and assembled correctly. Bearing housings must support reliable lubrication and practical maintenance. For oil-lubricated, non-pressure-fed bearings, provide adequately sized fill and drain connections. The drain should be valved and plugged so oil can be removed safely without uncontrolled leakage. Bearing housings should use replaceable labyrinth-type end seals and deflectors. Labyrinth seals reduce oil leakage and contamination ingress without creating the wear associated with contacting seals. Deflectors help keep water, dust, chemicals, and external contamination away from the bearing housing sealing region. Now move to the ring liquid system. The ring liquid forms the compression cells, seals internal clearances, removes heat, absorbs or condenses process constituents, and carries contamination out of the machine. Its flow, temperature, cleanliness, and composition directly control machine performance. Choose deliberately between once through, partial recirculation, and total recirculation operation. A once-through system is simple, but it may consume large quantities of liquid and create significant treatment or disposal requirements. Partial recirculation reduces consumption, but requires temperature control, purge management, and contamination monitoring. Total recirculation minimizes makeup demand, but it depends on reliable separation, cooling, purge control, level control, and recirculation pumping. There is no universally correct arrangement. The correct system depends on liquid availability, environmental restrictions, contamination, heat load, process compatibility, and operating philosophy. If a separate ring liquid pump is required, use a properly engineered centrifugal pump. Select it for the actual ring liquid properties, temperature, contamination level, static head, separator pressure, required flow, pressure losses, and available suction head. Do not size it using only a nominal package flow. The pump must operate with adequate margin across the complete operating range. Loss of ring liquid flow can cause rapid vacuum loss, overheating, unstable operation, seal damage, and equipment shutdown. The separator must handle gas and liquid during startup, normal operation, rated duty, turn down, and upset conditions. Its level range must prevent liquid carryover into the downstream gas system and prevent gas entrainment into the recirculation pump. Cooling duty must maintain the specified ring liquid temperature at the maximum expected heat load. If the cooler is undersized, fouled, bypassed, or deprived of cooling medium, ring liquid temperature rises, vapor pressure increases, and the achievable vacuum deteriorates. The machine may appear mechanically healthy while process performance steadily collapses. Controls and instrumentation must protect performance, containment, and equipment integrity. The control philosophy should address suction pressure or vacuum, discharge pressure, ring liquid flow, ring liquid temperature, separator level, bearing temperature, vibration where required, seal condition, motor current, and driver status. Cause and effect logic must be explicit. Low ring liquid flow should alarm and, where necessary, trip the machine before damage develops. High ring liquid temperature should warn the operator that vacuum capability is declining. High separator level should prevent liquid carryover. Low separator level should protect the recirculation pump from gas ingestion, cavitation, or loss of suction. High discharge pressure is a serious hazard. A blocked, restricted, or incorrectly lined up discharge can overload the machine, increase absorbed power, raise temperature, and damage the separator, casing, or discharge piping. Startup sequencing must confirm correct valve lineup, ring liquid availability, separator level, cooling availability, seal system readiness, open discharge path, electrical permissives, and downstream readiness. Do not allow the driver to start merely because a start command has been issued. Shutdown logic must also be engineered. Consider isolation, depressurization, draining, flushing, purging, residual liquid, contamination, freezing risk, and restart conditions. Drivers and transmissions must be selected for the maximum credible load, not only the normal absorbed power. Consider startup torque, maximum gas load, ring liquid density, cold liquid viscosity, discharge pressure excursions, process fouling, recirculation conditions, and adequate design margin. Verify motor rating, starting method, hazardous area classification, speed, service factor, coupling selection, coupling guard, alignment tolerance, and torsional behavior where relevant. The baseplate and coupling arrangement must preserve alignment during lifting, transport, grouting, piping connection, and thermal operation. At the same time, it must allow practical removal of the motor, coupling, seals, bearings, and machine components during maintenance. Package piping must comply with the applicable process piping design basis. Vendor-supplied piping is still process piping. It should never escape project engineering review merely because it is mounted on a skid. Review material class rating, flange rating, branch design, corrosion allowance, gasket selection, valves, supports, slopes, drainage, venting, flexibility, insulation, heat tracing, vibration, and accessibility. Instrument piping and hookups must measure the intended variable, remain accessible, avoid unwanted gas or liquid traps, and withstand machine vibration. Poorly located pressure taps, unsupported impulse lines, blocked connections, and incorrectly sloped tubing can produce false readings and dangerous control responses. Inspection must be planned before fabrication begins. Do not treat inspection as a final visit after the package has already been assembled. Agree hold points, witness points, documentation requirements, material verification, dimensional checks, balance records, seal documentation, alignment data, weld examination, instrumentation checks, and acceptance criteria at the purchase order stage. The casing hydrostatic test should be accepted only when there is no leakage and no seepage through the casing, joints, or connections during the specified holding period. Confirm the test pressure, test medium, temperature, venting, gauge calibration, stabilization period, inspection method, drainage, drying, and preservation. Even slight seepage indicates a containment weakness. It should not be dismissed as cosmetic. Finally, conduct a continuous mechanical running test at normal speed for a sufficient period to demonstrate stable operation. Verify vibration, bearing temperatures, noise, leakage, lubrication, seal behavior, speed, alignment stability, and overall mechanical integrity. Where the package includes a control system, demonstrate the control system during the running test. Do not accept a panel merely because it powers up. Prove alarms, permissives, trips, start and stop sequences, local controls, indications, shutdown logic, and relevant package interfaces. A sustained running test allows temperatures to stabilize, leakage paths to appear, lubrication defects to emerge, alignment behavior to settle, and intermittent control problems to become visible. A brief rotation check cannot reveal these issues. The engineering lesson is direct. A reliable liquid ring vacuum pump or compressor is created by defining every operating condition, agreeing fluid properties, eliminating weak hazardous service connections, controlling piping loads, selecting maintainable seals and bearings, enforcing balance and vibration limits, engineering the complete ring liquid circuit, protecting the package with effective controls, and proving containment and operation through disciplined testing. When you review one of these packages, do not ask only, will it meet rated capacity? Ask whether it will start safely. Ask whether it will remain stable at minimum, normal, and maximum load. Ask whether it can maintain the required ring liquid temperature. Ask whether the separator can handle every gas and liquid condition. Ask whether piping loads can distort the machine. Ask whether the seals can contain the process. Ask whether the instrumentation can detect failure early. Ask whether the control system will act before damage occurs. Ask whether operators can drain, vent, flush, isolate, and restart the package safely. Ask whether maintenance personnel can access the seals, bearings, coupling, instruments, valves, and cooler without dismantling half the installation. Then ask for evidence. Has the casing demonstrated complete pressure integrity? Has the machine completed a stable continuous running test? Have vibration and bearing temperatures stabilized within acceptable limits? Have the controls actually been function tested? Have alarms, permissives, and trips been demonstrated? Have site piping loads and alignment tolerances been checked? Those questions separate a purchased package from an engineered system. That is the standard you should apply to every liquid ring vacuum pump and compressor you specify, review, inspect, commission, operate, troubleshoot, or inherit.